We'll be talking about bursty star formation histories.
All right. Good afternoon. So my name is Zheng, coming from Purple Mountain Observatory in Nanjing. So thanks to this organizer for giving me this chance. This is my first time to be at Santa Cruz. Nice campus. I like it. I'm going to talk about some work done in the past few years with my colleagues and our students. They are very good students. And we work on a few topics, but today I'm going to talk about the first part about the star-forming galaxies. And actually, this is newly established group. And we have a faculty position available. If you are interested, or postdoc position as well, you contact me. Yeah. Sorry? Nanjing, yeah. Yeah, this website you can visit. Well, about star-forming galaxies, we know that there's two modality of a galaxy population, quiescent and star-forming ones. For star-forming ones, we have a very tight correlation between stellar mass and the star formation rate. It's called main sequence. And the new results, the version of the main sequence already have several versions. Before it was a straight line, and later on the broken power law. Now it's bending curve for the main sequence. Well, so the main goal for characterizing the main sequence is the normalization of main sequence at each cosmic epoch, and also the slope and the shapes of curve, and also the scatter of the main sequence. So the scatter, what the scatter can tell us, is that driven by the measurement error or the true burstiness of the star formation history for star-forming galaxies. From here, the early version of the main sequence, you see the star-forming galaxies spread widely, especially at spent end, at the low mass end, and good tighter at high mass end. That's a true story for the main sequence. And actually, so if you see the left version for high redshift and the dispersion, get confused because it's very sensitive to selection of the sample. So the question of my talk focused on is what controls the scatter main sequence? Does it change with the location of the along the main sequence? Each star-forming galaxy, experience its star formation history, whether it's smooth or bursty. It can tell us about the physical processes in the evolution. So, for example, the left plot is from a fair simulation. So here in the audience, there are many astronomers work on simulation using this simulation code. And here the burstiness is triggered by stellar feedback, by supernova. On the other hand, the right plot shows actually by other process, computation of different time scale, and end up with burstiness too. And moreover, actually, so not only stellar feedback, but also other processes, including the variation in accretion rate, accretion inflow. Okay, it's not smooth process. Maybe once you have a minor merger, it supply a large amount of gas. Then you got a burst, small burst. And also, because of the gravitational disturbing, and it might trigger a small burst as well. So such a physical process may shape the star formation history. So by looking at population of similar physical process, we actually can trace how the can recover to some extent the burstiness of the star formation history. So we already know that actually the stellar feedback is quite, it is dependent on stellar regime. I mean, the significance of the feedback, its effect, how strong on its star formation activity, it's actually rely on the mass regime. For most massive galaxies, stellar feedback might play a little role, but for the low mass and the supernova feedback may heat up all gas and stop further star formation. And also there's the time scale related to the feedback effect. You know, for a long time scale, it's actually the feedback heat up the gas in the halo, and which affects the gas supply to upcoming star formation. But the short time scale is just, you know, supernova heat up the surrounding star formation region and surprise the star formation. Yeah. So when we talk about the measurement error on the dispersion of a main sequence, actually, so many questions come from now how large the measurement error could be. Is that to account for half or larger fraction of the dispersion along the main sequence? Indeed, if you use the same methodology measuring either stellar mass or star formation rate, the scatter within the sample could be very small. For example, like if you use different methodology, the scatter could reach larger than 0.2 DAX. But if you use the same methods to use different type of galaxy, and the scatter is at the order of 0.1 DAX. Similar for the star formation rate estimate. If you use UV plus infrared or H alpha plus 24, such indicator, the best one, count both unobscured and obscured star formation rates, which give you very tight correlation. That means the photometric error here is negligible for your estimate of a burstiness or scatter among the main sequence. Different indicators, star formation indicator, trace star formation on different time scales. For example, H alpha trace sensitive to the most massive young stellar population with age at 10 million years, but UV plus infrared could trace longer star formation. So here I would remind you that actually we must use infrared plus UV to measure the infrared, because other galaxies complex system, so some star formation region could be completely obscured, so no Barlow line escape, so you can detect them, do the extinction correction. Only way is use the infrared to trace the obscured star formation. And this is version, the extinction could change by more than order of magnitude. So with Barlow decrements, you cannot accurately estimate the extinction. Here for blue selected lemon break galaxy, the extinction could change at a given fixed stellar mass, can change by larger than 1 order of magnitude. Imagine if you do the correction using some kind of approximation, the result could be maybe differ far from the truth. So for example, here using the atmosphere spectra, H alpha, using extinction corrected H alpha, gave a main sequence with slope much lower than unity. It's a slope of 0.6. This is because many massive, heavily star forming galaxy totally missed by H alpha observation. So they are like submillimeter galaxies. They don't have a strong Barlow emission line. So the best way to do this is use infrared plus UV to trace star formation rate. Here an example how good this star formation indicator can do. If you correct the evolution, redshift evolution effect on cosmic star formation rate, and also select as few as possible, just only disk galaxy, and you end up with a very tight main sequence with scatter only as low as 0.15. So this is also tell us actually star forming galaxy, they behave very similar. And it speed up. So we worked on Cosmos data site. Thank you. Using 24 macron from SPISA and UV from the SED fitting, give a main sequence measurement for redshift 0.7 by correcting all the cosmic evolution effect. And also we try to starting the low mass galaxy at faint end because 24 macron limitation is unable to detect at 24 macron. We try hard, and especially for those undetected star-forming galaxy at faint low mass end, we did some kind of mock recovery of the scatter. So we assume here by starting we get average 24 macron measurements at the low mass end. We try to assume that actually the 24 macron flux follow a log normal distribution like the high mass end, then adding to our measurements. It turns out actually the infrared for low mass galaxy, the infrared not dominates the star formation rates. It's dominated by the UV luminosity. So you play the game, and you can figure out actually the scatter in specific star formation rate is pretty small, and this is main sequence at redshift 0.7 by using UV plus infrared, and we arbitrarily shift the log normal distribution of the specific star formation rate, and you can see that for high mass star forming galaxy, the distribution is broader with a bigger scatter. For low mass ones, the distribution is much narrower, significantly. Actually, we can resolve the difference between the two populations. Actually, it's free from whether how big 24 macron dispersion you add. So from this exercise, we learned that actually at this mass regime, about 9.5, the dispersion of a main sequence actually increased with the stellar mass. Same exercise you can do for low Z star-forming galaxies. So here's the latest version of the local main sequence. So don't use this one. This is a linear slope. And if you use 24 macron plus H alpha, it gives a quite small slope, means the specific star formation rate for high mass star forming galaxies is actually lower than that for low mass star forming galaxies. Yes. If you plot the dispersion, and you can find that for the right curve, the high mass star forming galaxy, the distribution is broader with a bigger dispersion. Again, for low mass star forming galaxy, the distribution is narrower with smaller dispersion. Left panel shows the dispersion as function of stellar mass, because for local ones, we have the image to decompose them into barge and disk components. We are able to replace the specific star formation rates with disk galaxy. So replace the total mass with the disk again. So you find actually the specific star formation rate dispersion increase with disk mass. Interestingly, if you select star forming galaxies by morphology, if they are pure disk dominated ones, their specific star formation dispersion remain nearly unchanged over stellar mass nearly 1 order of magnitude. What does this mean? So So let's come back one slide later. So if you now resample the star-forming galaxy using B over T, barge to total ratio, it turns out once you have big barge at center, the star formation in disk components could change by order of factors 2, 3, 4. That's the biggest variation compared with the other the subsample with smaller B over T. So here we conclude that actually B over T, the parameter present of a barge and also the galaxy itself, both broaden the specific dispersion. It's understandable. Here, add one more is we try to examine the specific star formation rates at the center and the outer part, finding actually those high mass star forming galaxy actually contain more massive barges, which affect star forming activity in disk component a lot. So if you compare it with the simulation result, because different star formation rate indicator trace the variation at different time scale, H alpha plus infrared actually trace starburst at a time scale here 10 millions, and using here our star formation indicator traced. From simulations, the feedback from supernova will heat up the gas in the disk and also in the halo, and it will cause a strong burstiness. And this is a function of stellar mass, so it becomes larger at the smaller halos. But indeed, in observation, we found exactly the opposite. Here, it's a little bit misleading because this is a pure stellar feedback effect, right? But for high mass galaxies, you have not only stellar feedback, but also other effects like barge or halo-driven effects. If you create a satellite, then it will trigger a burst, but it's not because of the stellar feedback. And so the purple line is the fire prediction for stellar feedback. Yeah, here is an example that's actually for the simulation. If you make a fair comparison with observation, you need at a high mass end, you need also count not only stellar feedback, but also other effects so that we can make a good comparison to see whether the simulation are consistent with observations. That's now the burstiness of the scatter of the main sequence can add strong constraints on simulation for high mass end. Of course, we ideally want to push this to fainter end, but it's very challenging. For PUDISC, come back to the PUDISC, the constant dispersion, what does that mean? So in my mind, I can imagine this picture. So for disk galaxies, the outflow from supernova go to the perpendicular to the disk plane, and the star formation happen in subgalactic scale. So the ongoing star formation will not be substantially affected by starburst in another place. So still ongoing star formation survive in another part of the disk plane. That's how I see the constant dispersion for PUDISC, over 1 order of magnitude in stellar mass. That's a take-home point. I just still have 2 minutes. I would like to just go quickly and still have 2 slides to show you. Yes. So currently, from observation, the dispersion of the main sequence can reflect the burstiness of star formation history. And secondly, actually, when you address the feedback effect, you need to high mass end exactly not only stellar feedback, but also other effects actually lead a bigger, larger dispersion in among the main sequence. The third part is we perhaps miss some components in simulating galaxy like PUDISC galaxies. This morning, we heard several talks on ultra-diffuse galaxy. Actually, this is a dwarf galaxy with relatively smaller halo and very sensitive to stellar feedback. That's the ideal target to study now how stellar feedback affect on the ongoing star formation. So by selecting now survey the sky and find the nearby targets, we can do further study in detail. But firstly, we look into a deep fields around a compact group and finding actually there are quite many such UDGs. Here is the image taken with a 1 meter wide field telescope, but with a 4 meter Maya telescope, you have a higher, better resolution image. Still, they look very diffuse. And indeed, we found nearly 1/3 of them actually blue galaxy, UDG, quite blue. This is the color magnitude distribution. The background green data point is actually Sloan galaxies. And we also plot the H1 selected galaxy in cyan symbols. They appear quite similar in color space. We found one interesting target with existing VRA observation. It turns out this is a gas-rich galaxy with much more gas than stellar mass. And it turns out that actually UDG population overlap with H1 select population. This color diagram for UDG. And so if you have a strong emission line, so the targets will appear now to that regions. From morphology shape, all appear like round, and you don't see very H1 projected UDG. It might be some kind of selection effect because once you H1, the surface brightness will be brighter, but we need further careful study on this effect. So far, the 89 candidates show the excess ratio actually above, almost all above the 0.5. They appear right. And abundance follow the same linear correlation with stellar halo mass. This is my last slide. I stop here. Thank you. Thank you for. See again, sorry. No, we don't have gas, especially gas, molecular gas information. No, we don't have that.
So in the last slide that you showed us, the one just before this, or maybe it was the very last one, you showed the distribution.
This one?
Yeah, this one. The axis ratio distribution. And this sharp drop near the large axis ratio, Andy Burkert emphasized that that's inconsistent with disks or disky shaped objects and tends to point toward collate. Do you agree? This is actually a stronger effect than in the large sample from Coma.
Right. So if for the disk galaxy, the axis distribution would like that observation effect would turns out. Right, a higher fraction. Yeah. But here we don't have. Yeah. I would like to confirm this because most of them appear like spheroidal rather than disky. Then that would be about some kind of object similar to primordial galaxies, I would say. Wow.
But they're spheroidal rather than disky was the point that Andy made, and your statistics are even stronger, although it's a small set.
Right. Good to see. But here is some kind of a selection effect. Now, perhaps move to here because
Well, that's what you get if they're spheroidal. If they're basically outlet.
Yeah.
Then you don't get a lot of really small axis ratios.
That's right. Yeah.
Okay, let's thank XianZhong again.